Good morning to one and all. In the last few lectures, we have been discussing strain gauges. We saw the principle of operation of strain gauge. We saw some bridge circuits also. We saw one arm bridge. We saw two arm bridge. We saw four arm bridge. And we also saw how the strain gauges should be arranged in the Wheatstone bridge circuitry so that we can get some meaningful output. Just to recollect, the strain gauges which are subjected to same nature of strain or same kind of strain, let us say tensile strains, those should be placed in opposite arms. And those strain gauges which are having opposite natured strain means if the one is subjected to tensile strain and the other is subjected to compressive strain in the Wheatstone bridge, these dissimilar or opposite natured strain gauges should be placed in the adjacent arms. We briefly started off with the main topic, that is we were studying the force transducers or load transducers. So one of the transducers is strain gauge load transducer. Up till now we saw the principle of strain gauge. Now we'll see how these strain gauges can be used to measure force or load. Now there are two types of load cell, strain gauge load cells. One is cantilever beam type strain gauge load cell and the other is cylindrical specimen type strain gauge load cell. Now as you can see in the figure, we have a cantilever beam which is having a rectangular cross section. The cross section is not shown here. It is having a rectangular cross section. The thickness of the beam, let us call it as T. This thickness is T, and the width as a section width is B. Okay, so this cantilever beam is subjected to this kind of force. Now what kind of load this is, what kind of force it is? It's called as bending load. Now when the beam is subjected to bending load, if you recollect in strength of materials we have studied, the beam will have one neutral axis. So at neutral axis there will not be any stresses or strains. So above the neutral axis and below the neutral axis we see the more intensity of stresses and strains. Now in case of this rectangular cantilever beam, what happens is when it is subjected to loading, the top surface is subjected to, as you can see, it is subjected to tension. So tensile stresses are induced on the top surface and those tensile stresses get converted or get translated into tensile strains. So the top surface is subjected to tensile strain, whereas the bottom surface of the beam is subjected to compressive stresses or compressive strains. So these are opposite nature strains, those are developed in a cantilever beam. Remember, this is a bit exaggerated figure. The beam will not be deflected that much. Just to make you understand the concept, more deflection is shown here. So when I applied a bending load, the top surface strain gauge will undergo plus epsilon, which will lead to plus delta R, and the bottom surface strain gauge will be subjected to minus epsilon, that is minus delta R. Okay, so my load, if you look at the load, F is acting at this beam length of L, isn't it? F is acting at this beam length is L. So this F is acting at this L. Let us try to find out the theoretical strain first of all. Okay. So we have studied these things in strength of materials just to recollect. So how much will be the bending moment on this cantilever beam? This F into L will be the bending moment. Maybe Newton millimeter would be the units. The force is in Newton and the length of the beam L is in millimeter. So I am applying a bending moment of F into L Newton millimeter. Now to this bending moment, how this cantilever beam would react? This cantilever beam, as I said, is has a rectangular cross section which has got width B and thickness T. Please be attentive. So what will be the section modulus of this rectangular cross section? Now section modulus Z is equal to I upon Y. Y is the distance from the neutral axis, distance of the external or outer fiber from the neutral axis. Neutral axis will be midway. So the distance of the outer fiber of the top surface is, if the thickness is T, the distance of the outer fiber from the neutral axis is T by 2. And distance of the lower surface from the neutral axis is also T by 2. Isn't it? So how much will be the Z value? I upon Y. So it is, what is I for rectangular cross section? Yes, 1 by 12, 1 by 12 bt into cube, b into t raised to 3 is the I value. And what is the y value? Y value is t by 2. So ultimately what will happen? 1 by 12 will get reduced to 1 by 6. B will remain as it is. And t will be converted to this t cube by t by 2, isn't it? So it will become, the section modulus for this rectangular cross section will be 1 by 6 bt squared. Isn't it? 1 by 6 into bt squared is section modulus Z. Now, how as per bending equation, how do you find out the bending stresses? M by Z will give me bending stresses. Now, how much was bending moment? F into L Newton millimeter divided by Z. Z is 1 by 6 bt squared. And what are the units of Z? B 1 millimeter, T square is millimeter square, so millimeter cubed. So stress sigma B, bending stress, will be equal to M by Z. So Newton millimeter divided by millimeter cubed. And what I get? Ultimately the units will be, bending stress sigma B will be equal to M by Z Newton per millimeter square. Isn't it? Now we also know, now we have got stresses induced in this rectangular cross-sectional cantilever beam. Now, how to get the strain? We know stress by strain is Young modulus E. So strain will be equal to stress by strain sigma upon epsilon is equal to E. So epsilon will be equal to sigma upon E. So whatever bending stress I have obtained, theoretically we are doing the calculations, divided by E gives me strain. So that will be theoretical strain that is induced in this cantilever beam, isn't it? Now, my strain gauge, what it does, so whatever experimentation we can do on this strain gauge, we can carry out the experimentation like this. First of all, for different loads, we find out different stresses, and for different loads, we also find out different theoretical strains. And practically also what we do is, we mount the strain gauges on top surface and bottom surface, and we measure the output voltage as we discussed in the last class. From the output voltage, we can find out what is the experimental strain that we have obtained. And these can be compared for the correctness. Okay. Now coming to the bridge circuitry. If you recollect, in the last lecture we had said opposite natured strain gauges should be in adjacent arms. Isn't it? This is Wheatstone bridge. This is the supply voltage that I give, maybe if 6 volt DC I give to the bridge, and at these terminals I measure the output voltage, maybe dV or delta V. That is the output voltage that I obtain because of bridge imbalance. So once I apply the force, just to repeat, the top strain gauge is subjected to tensile strain, so it will have plus epsilon, and the bottom strain gauge is subjected to compressive strain, that is minus epsilon. The top strain gauge will be subjected to plus delta R, and the bottom strain gauge will be subjected to minus delta R. So these will be in adjacent arms. So opposite nature strain gauges in adjacent arms. Now all these, now see, the resistances of all the arms are initially kept at same value. I select the strain gauge. If I select a strain gauge of value 120 ohm, this will also be of 120 ohm. This fixed resistor will also be of 120 ohm. So initially the bridge is balanced. Now once I load it, what happens? This is delta R is happening here because of tensile strain, and there is because of minus epsilon, minus delta R will be there, and the bridge gets unbalanced, and I see the output voltage. Now that output voltage, if you remember, V out divided by V in for a 2-arm bridge. You can go back to the last lecture and just make a note of it. For a 2-arm bridge, V naught or the output voltage, V naught upon Vn is equal to, or delta V upon Vn is equal to 1 by 2 or 1/2 gauge factor into how much it was? Gauge factor into epsilon, isn't it? Now out of this, what are known to us? Epsilon is not known to me, but output voltage I can measure. Output voltage I can measure here. Input voltage I know how much I am applying. So V naught or V output and V input can be measured. So V naught upon Vn is equal to 1/2 into gauge factor. Now gauge factor, as I said, I know the gauge factor also initially. If it is 2, so gauge factor will be 2 into epsilon. So I saw epsilon is unknown. So that epsilon will be epsilon experimental, isn't it? So epsilon experimental will be equal to V output into 2 divided by V input into gauge factor. So all the parameters are known to me. For different loads, I'll be getting different output voltages, and for different output voltages, I can find out how much is the experimental strain. Now, after knowing experimental strain, from once again Young's modulus equation, from strain I can find out how much is stress, isn't it? Stress upon strain is E. So strain I know, E I know, I can find out how much is the stress. Now once I know stress, I know how much will be the force. Now stress, if you just opposite way we have to go. This is the bending moment. So stress is m by z. So z is known to me, isn't it? So z is known to me. So whatever stress value I get from experimentation into z gives me bending moment. The bending moment is F into L once again. So L I know. So stress into Z divided by L gives me my experimental strain value, experimental force value. Sorry, experimental force value. So this is how my strain gauge load cell can give me the force measurement. So we need balancing circuitry for that, and we need some amplifying circuitry also. We need some filtering circuit also. Those details can be worked out later on. Just let us try to understand how this cantilever beam type load cell can be used to measure the load or force. So wherever in practical situations, wherever I want to measure the force applied, so the force acting element, beneath that force acting element or the reacting element, I'll be having this kind of beam type, cantilever beam type strain gauge load cell. I can have a connecting rod in between. Suppose I am applying a load on the platform. The platform is above. I'm applying the load on the platform. So the platform will be connected with a bar at the end of this cantilever beam. So that force that I'm applying will be transmitted to the cantilever beam, and I'll be getting output voltage, and the voltmeter can be calibrated directly to indicate the force, isn't it? So this is how this cantilever beam type strain gauge load cell can be used for measurement of force. So just read out: with no force applied, left figure, no force applied to the test specimen, both strain gauges have equal resistance and the bridge circuit is balanced. So there is no output. However, see the right hand figure. When a downward force is applied to the free end of the specimen, it will bend downward, stretching gauge 1, that is subjecting gauge 1 to tensile strain, and compressing gauge 2. So applying, or I'll be having compressive strain at the bottom surface. So this is how this cantilever beam type strain gauge load cell can be used as a force transducer. Hope things are clear. I'm going a bit faster. I'll be sharing you notes also, the equations also we can recollect, and if required, I'll send you the notes related to calculations. We have got the test setup for different types of cantilever beam type strain gauge setups. So we can carry out whenever we start our classes in the college. We'll conduct experiment. We'll find out the experimental strain and theoretical strain, and from that we'll find out the correctness of this strain measuring system. So we'll find out from experimental strain, we'll find out experimental force applied, and from theoretical strain, I can find out what is the theoretical force applied. Force, in fact, in the laboratory, I know if I'm putting a weight of 1 kg, I know how much is the force that I've applied. I have to just check whether my strain gauge load cell is indicating 1 kg or not, isn't it? So that is very much possible. Moving further, the second type of strain gauge load cell, that is cylindrical specimen type strain gauge load cell. Now these are a bit widely used strain gauges. Whatever weighing platforms we see in jeweler shop, in tea shops, grocery shops, small weighing platforms, just you see the stainless steel plate, but beneath that I can have cylindrical columns like that. I can have one single column, or I can have 4 columns at the 4 faces of that plate. The steel plate you see, and the digital indicator that you see, which indicates the weight or force. So beneath the platform cha khali 4 pillars, cylindrical pillars. This kind of pillars will be there. Hollow cylindrical pillars, of course, are to increase the sensitivity of the load cell. Hollow cylindrical pillars are used. Or sometimes if the weight or force that is to be measured is the range is very small, that is 0 to 5 kg. Single column cylindrical type strain gauge load cell is sufficient. If I want to measure larger amount of force, 20 kg, 100 kg, I go in for multiple columns of cylindrical specimen type. See here. So above this cylindrical top surface, there will be the weighing platform. That's what we see, and everything is there beneath the box. You just see the display. So if you open up the display, you'll find this cylindrical specimen on which these strain gauges are mounted. So the load is applied here, and what you can see here. Now when I apply a load, just be attentive a bit. When I apply load, the cylinder will be subjected to compression. So what happens? This is the longitudinal section and this is the lateral section. When this is compressed, what happens? The cylinder will try to expand. So the lateral strain will also be there. So when I apply a compressive force, so compressive strain will be induced in these longitudinal strain gauges. These strain gauges are longitudinally mounted. And as the compressive load is applied, the cylinder will tend to expand, isn't it? When it tends to expand, what does that mean? There will be circumferential stresses or hoop stresses. So the strain gauges are mounted like this. Okay. So longitudinal is like this and lateral is like this. So when the cylinder tends to expand, what happens? These strain gauges which are mounted laterally will expand. Whereas these, when I apply a compressive load, these longitudinal strain gauges will be subjected to compressive strain minus epsilon or minus delta. Whereas as these lateral strain gauges will be expanded or the cylinder will be expanding, so there will be lateral strain which is increasing. So these strain gauges will be subjected to plus epsilon, plus mu epsilon, of course, because it is a lateral strain. Because mu is Poisson's ratio, which is lateral strain upon longitudinal strain. So I will be getting this lateral strain in the form of mu epsilon. Okay, so ultimately there will be plus delta because this resistance is increasing. Why this resistance is increasing? Because these strain gauges, because of expansion of the circumferential surface, because of expansion, these strain gauges will be subjected to increase in length. So when there is increase in length, there will be increase in resistance, isn't it? So R2 and R3 will be subjected to plus delta R, and R1 and R4 will be subjected to minus delta R. We are talking about compressive strain, isn't it? Compressive strain, these are subjected to longitudinal strain gauges. These are diametrically opposite. Remember, R1 and R4 are diametrically opposite, and these R2 and R3 are also diametrically opposite. Those are mounted like that. So it's a 4-arm configuration, isn't it? 4 resistors, 4 strain gauges I'm using. So for compressive load, I'll be having compressive strain in R1 and R4 and lateral strain, which is tensile in nature, in R2 and R3. So R1 and R4 are of same nature, compressive strain. So R1 and R4 are in opposite arms. Just recollecting the convention, the same natured strain gauges should be in opposite arms. R1 and R4 are of same nature. What nature? In compressive loading, compressive strain. So these are in opposite arms. How about R2 and R3? These are subject to lateral strain, which is increasing, isn't it? Plus mu epsilon, plus delta R, plus delta R. So these are of same nature, isn't it? Both are expanding. So this same nature will also be in opposite arm. So same natured strain gauges will be in opposite arm. Whereas opposite natured, this is minus epsilon, this is plus mu epsilon. Minus and plus, these are opposite nature. These are in adjacent arms. Whereas same natured, R1 and R4 are in opposite arm. R2 and R3, same nature, are in opposite arms. Just think slowly and don't get confused. It's simple. Just to understand and remember. Now what will happen? Just think over now. This is the compressive load that I have applied. You try to understand if I applied a tensile load. Both ends I have outward arrows. And tensile load is applied on this cylindrical specimen. What will happen? When tensile load is applied, R1 and R4 will be subjected to tensile strain, isn't it? There will be increase in length, so plus delta R. And what will happen laterally? When I'm trying to pull the cylinder up, what will happen? The diameter will tend to reduce, isn't it? Diameter will tend to reduce. So the lateral strains will be of compressive nature. So I'll be having minus mu epsilon on R2 and R3 when I'm applying tensile load. So the arrangement of the bridge will remain same. R2 and R3 will always be of same nature. So R2 and R3 will be in opposite arms. R1 and R4, in the tensile cases, it will be subjected to tensile strain. R1 and R4 are also same nature. So those are also in opposite arms. So rest of the bridge circuitry is same. I have a switch, I have a supply voltage, I'll be measuring the output voltage. Now, if you go back to the last lecture, we had written equation for. Now this is a 4-arm active bridge or full bridge. Because why we call it as a 4-arm bridge or full bridge? Because all the resistances are replaced by strain gauges. So R1, R2, R3, R4 are all strain gauges. R1, R2, R3 and R4 are all strain gauges. So this is a 4-arm bridge. Now what is the equation for output voltage? Just try to recollect. V0 upon Vs or V input is equal to 1 into gauge factor into epsilon. Isn't it? So repeat. V out, output voltage upon input voltage, which I know 5 volt, 6 volt DC. Okay. So I put the switch on, conduct the experiment, apply different loads, known loads, measure the output voltage, and I put it in that equation. Output voltage upon input voltage is equal to 1, which is the bridge constant for 4-arm bridge, 1 into gauge factor, which is normally 2, into epsilon. If I solve this equation for epsilon, how it will be? V output upon V input or V supply into gauge factor will give me epsilon experimental. And once again, what is epsilon? Is the strain. So experimentally I can find out, and even theoretically I can find out. So this is a cylindrical specimen. Strain, stress upon strain is E. So E I know of this specimen material, E I know. I have just measured the output voltage and I have just got epsilon value. So stress upon strain is equal to E. So E I know, into strain I know. So I know stress in case of this cylindrical specimen. Force upon area, cross-sectional area, force upon cross-sectional resisting area is stress. So force will be equal to stress into A. Now what is stress? Stress is E into E, Young's modulus of velocity, into strain. So this is how I can find out theoretical force induced and experimental force induced. So this is how your cantilever beam type cylindrical cantilever beam type strain gauge load cell and cylindrical specimen type strain gauge load cell can be used for measurement of force or load. I think we should stop for today.